So when you're looking at the integral from a to b of f of x dx, what we're thinking of here, right, if you've got some function, f of x, and we're going from, say, a to b, as I think she's made pretty clear, you're calculating what we typically say is the net area below the curve that happens to be above the x-axis. So in less fancy words, all of the stuff that's above the x-axis gets counted as positive, and all the stuff that's under the x-axis and still between the x-axis and the curve gets counted as negative. So when we're calculating this, it's going to equal the red area minus the blue area. And that's kind of super important. So for example, if I was trying to calculate, say, the integral from negative pi over 2 to pi over 2 of sine of x. Well, we haven't talked about the fundamental theorem of calculus yet, so we don't know. There's a very nice, easy way to calculate this using antiderivatives. We're not there yet, but we can draw a picture. And if we draw this picture, we'll check it out. Sine of x looks like this. I know that sine of 0 is 0. I know that sine of pi over 2 is 1. I know that sine of negative pi over 2 is negative 1. And it looks like this. And the thing about sine is that it's an odd function. It has symmetry about the origin. So that this area here underneath the curve and this area here above the curve, those are exactly the same. And so they cancel each other out because this area gets counted as positive and this area gets counted as negative. So this integral happens to equal 0. And in fact, this is a true kind of thing for a lot of functions that are odd. In fact, for all, I shouldn't say a lot, all functions are odd. So another example of this would be something like, I don't know, the integral from negative 2 to 2 of x cubed. X cubed is an odd function. You can kind of graph it. I'm not great at graphing x cubed. Oh, let me turn down my, sorry, one thing. Let me turn down my adjustment for low light. That makes it a little easier for you guys to see what's on the board. Hopefully you guys can see. Also, no blurriness today, right? Things are looking all right? Yeah, okay, cool. You guys will let me know if it's blurry, I'm sure. So if I graph x cubed, which looks like this, which does have symmetry about the origin, meaning it's right. If you rotate it 180 degrees, it looks the same, just like this. If you rotate this 180 degrees, it looks the same. If I'm going from negative 2 to 2, we're exactly seeing the same sort of thing, that the area above the curve, the area above the x-axis that's below the curve is exactly the same but opposite of this area over here. So those cancel out. And the general statement of this property for integrals, which I don't think she actually got to, is that the integral from negative a to a of f of x dx is equal to 0 if f of x is an odd function. That is definitely a property we exploit all the time. So if you see something, like if I say, I'm going to ask you to find the integral from negative 7 to 7 of, I don't know, x to the 5th times the square root of x squared, let me be smart here, x squared plus 1. If I asked you guys to find this, this thing is hard to deal with. the point is that this function is probably an odd function. Now, it's less obvious this one's odd because it's hard to graph. So here's how you show a function is an odd function. So the question here is our function odd? Is f of x equal to x to the fifth times the square root of x squared plus 1 odd? To show it's odd, what we're really asking is f of negative x equal to negative f of x? Well, let's see. F of negative x is negative x to the fifth times the square root of negative x squared plus 1. A negative number to the odd power stays negative, so that's negative x to the fifth. But the negative thing to an even power becomes positive, so that's times x squared plus 1. Whereas negative f of x is, I just put a negative out in front and I get negative x to the fifth times the square root of x squared plus 1. Oh yeah, those are the same. So that shows that this is odd, which means this integral is 0. That's a very useful property. It's going to save us some time on some other problems. Yeah. Oh, sorry. Let's see what else have we got here. I don't want that. So let's talk about trying to find area under curves. So I want to evaluate the following integral. Integral from 0 to 6 of the absolute value of x minus 2. And while later on we might actually learn how to do this using the fundamental theorem of calculus, you probably won't even want to. Finding this is really easy if we just graph it. So a lot of things you can find the areas of just by graphing them. So again, what does this mean? This means the area under the y equals the opposite value of x minus 2, which looks like this. It's like your absolute value of x function shifted 2 to the right. So here's my absolute value of x minus 2. And then integrating, we're finding the area under this curve between x equals 0 and x equals 6. So I'm finding this area. Well, here's the thing. Those are shapes that we know how to find the area of. We've got a triangle there and a triangle there, and we know how to find the area of a triangle. So for this triangle, the area of that triangle is 1/2 the base, which is 2, times the height, which is also 2. Right? If I plug in 0, when I plug in 0, I get y equal to positive 2. The area of this triangle, well, it's again 1/2 the base times the height. The base here is 6 minus 2, right? That point there is 2, so 4. And the height, if I plug in 6 to the function, 6 minus 2 is going to give me 4 as well. So this area is 1/2 times 2 times 2, which is 2. This area is 1/2 times 4, which is 8. So this integral is equal to 2 plus 8, which is 10. So we can totally evaluate an integral just by using formulas for areas of things we know. And that's a totally valid way of doing it. Much like this next problem. Okay. Don't hesitate to jump in if you have questions or need me to slow down a touch. So let's see here. Let's say we want to find this integral. So calculate the integral from -5 to 0 of the square root of 25 minus x squared. In some classes, you learn how to actually anti-differentiate this. I don't think we actually covered this particular type of integral in this class, which is fine. It's no big deal. But we don't have to know how to anti-differentiate this function y equal to the square root of 25 minus x squared to be able to find the area under the curve. Does anybody know what kind of curve this is? Like what kind of shape this gives us?
Half circle.
It does give us a half circle. If you're having trouble seeing that, it becomes a little easier if you square both sides. Y squared equals 25 minus x squared, and then add x squared to both sides. Then it's a little more clear that this equation is a full circle whose center is the origin, whose radius is 5. This equation is the top half of the circle because y equaling a square root means y has to be positive. So yeah, this is exactly, this equation gives you the top half of the circle with radius 5, centered at the origin. So this point would be 5, 0. This point would be 0, 5. This point would be negative 5, 0. And then since we're integrating or finding the area under the curve from negative 5 to 0, we're starting at negative 5 and we're going just to 0. So we're finding that area there. Well, what portion of a circle is that? Well, that's 1/4 of a circle. So this integral is going to equal, or the area under the curve is going to equal 1/4 of the area of a circle with radius 5. So it's going to be 1/4 of pi times 5 squared, which we could simplify, right? 5 squared is 25 times pi over 4 is 25 pi over 4. So the point kind of this is that you can use known area formulas to calculate areas under curves. Another example, yeah, let's do one more example. So sure, let's do the integral from 0 to 4 of 1 plus 2x plus the square root of 16 minus x squared. So this one's a little trickier because we got something that's a straight line and something that's a half of a circle. And I don't really know how to, like, drawing this function would be a bit challenging. We don't have to, though. We can break this up. So this is where you definitely want to use the fact that if you have an integral of things added together, you can write it as the integral. In fact, you can break it up into 3 integrals. The integral from 0 to 4 of 1 plus the integral from 0 to 4 of 2x plus the integral from 0 to 4 of the square root of 16 minus x squared dx. The dx is important. I don't always say it, but it is important. It's literally like, it's the same, it's the continuous version of your delta x from your sum. So this dx is like the delta x. We really do need it. Another cool thing to think about is like, this is like your base of your rectangle, and this is like your height of your rectangle. This is your base, this is your height. This is your base, this is your height. Which is that your base is super duper narrow. So for each of these, we could draw a picture. Right, this one is the top half of a circle of radius 4. So this one right here, looks like that, except we're only going from 0 to 4, so we're really just getting this. That's going to equal 1/4 pi times 4 squared, which is just going to be 4 pi. This part here, let's see, we can draw this one too. I know how to draw 2x. Y equals 2x looks like that. I'm going from 0 to 4. So I'm getting a triangle. The area of that triangle is 1/2 the base, which is 4, times the height, which I have to plug in 4 to my function to find the height. I plug in 4, I get 2 times 4, which is 8. So 1/2 times 4 times 8 is going to be 16. And then here, for this one, I'm just going to have a horizontal line. So here's y equals 1. The area under the curve from 0 to 4 is just going to be the base, which is 4, times the height, which is 1. Or if you wanted to use the formula she was talking about in class, the area is the function constant C times the B minus A, the width of the interval, which in this case is the constant, which is 1 times 4 minus 0. Right, so if you have a constant function, the area under it is just the width of the interval times the height, which is the constant function. So our total answer here would be 4 plus 16 plus 4 pi, which I would probably write as 20 plus 4 pi. And that's probably the easiest way to do this problem, even if you know other stuff later. Maybe not this middle part. Maybe this middle part's slightly easier to do a different way. But these two parts for sure, that's the easiest way to deal with them. I feel like, oh yeah, I know what I feel like I'm skipping something. Not really skipping something, I'm just, sure. Let me look at one other thing here. Yeah, it's okay, we'll come back to that. Yeah, we should definitely talk about that. Okay, cool. Yeah, all right. So I think, so in case you're curious, the things I've said so far pretty much cover how to do problems 1 and 4 on your homework. And yeah, I would say that's kind of it so far. All right, so yeah, let's do this. Not that I'm specifically like covering the homework, but it's good to be aware that like what we are learning, what we're doing in this class will be helpful so that you can actually do your homework. The last example I wanted, or not the last example, the next example, I wanted to show you something. So at the end of the class, she was talking about the this rule, which is that if f of x is between two constants, and we use little m to represent the minimum value and capital M to represent the maximum value, then it's also true that m times b minus a is less than or equal to the integral from a to b of f of x dx is less than or equal to m times b minus a. Now, I feel like writing the formula this way actually really kind of does you a disservice. Because really, this is just the same as, this is really the same information as this other rule. So here, I don't remember what the numbers were, but there was a rule that was before this which said this. If f of x, I don't remember which one was smaller. If f of x is less than or equal to g of x, it might have been written in the other order, it's okay. Then the integral from a to b of f of x dx, I should say, if f of x is less than or equal to g of x for for a less than or equal to x less than or equal to b. So if this is less than this, at least between a and b. Then the integral of this, or the area under this curve, is less than or equal to the area under that curve. That's all this rule is saying, because this right here, this m times b minus a, is the integral from a to b of the constant m. Right? When you integrate a constant, or when you find the area under a constant, you just get that constant times the length of the interval. Just like we did here. When we find the area under this constant, we just got the constant times the length of the interval. Same deal over here. This here is exactly equal to the integral from a to b of capital M. So we're really just applying this rule again. We're saying, oh, if f is less than m, then the integral of f is less than the integral of m. If f is bigger than little m, then the integral of f is bigger than the integral of little m. That's all we're really saying here. But let's do an example. I feel like there was one other piece that I wanted to say here. Oh, no, okay, we're good. So a way we could ask a question so that you would have to use this property is the following. Definitely going to edit out the crying from the video when I post it, just so you guys know. I don't think there's anything important that happened in the beginning of class. So we wanted to verify that 2 is less than or equal to the integral from -1 to 1 of the square root of 1 plus x squared, and then that's less than or equal to 2 square roots of 2. And so the idea here is that yes, I'm totally cool with crying. Like, I try not to cry on camera, right? That's usually the goal, but it's okay to cry on camera. It's an emotional time of, I want to say, the year, the world, our lives. It's an emotional time. That's all what I'll say. So something we need to do this problem is that on the interval from -1 to 1, we can see that this function, the square root of 1 plus x squared, is definitely going to be bigger than or equal to 1. Right? 1 is the smallest this could be when x is 0. And it's definitely less than or equal to the square root of 2. Right? When x is 1, that's the biggest it can be, and it's equal to the square root of 2. I can also draw some graphs. So this, I should point out, right? This is acting like my little m, and this is acting like my big M. So here are the pictures I want to show you. I'm going to try and draw some good pictures here. Yeah, I can draw some good pictures. So here's -1, here's 1, here's m equal to 1, little m equal to 1, and here's the area. Well, that area is definitely 2. And then on the right side, we have 1, 2. Square root of 2 is about 1.4, so I'll try and draw it there. It's maybe like there. There is capital M equal to the square root of 2. And the area under this curve, well, again, it's exactly, it's a rectangle, right? The area is base times height. So that's going to be the base, which is a length of 2, times the height, which is square root of 2. And then this function, the square root of 1 plus x squared, I'm going to try and draw it so it looks good. My drawing skills, you know, I could have just used Desmos. That might have been nicer. Oh, well, you guys can see it. Okay, so here's what we've got. So my curve, when x is 0, square root of 1 plus 0 squared is 1. And then when x is 1 or -1, I get the square root of 2 value. So it kind of looks like that. And so all we're saying, right, that for this function, f of x equal to the square root of 1 plus x squared, this area definitely is less than that area, if assuming I've drawn like this is the same height here. And that's less than that and bigger than that, right? The part it's bigger than is right there. The part it's less than is that big thing right there. So that is the comparison rule test. I think it's the comparison test rule, sorry. The comparison rule for integrals. Right, if you've got, or I think that's the other one actually, but this is essentially the same rule. Yeah. And we definitely, so the reason people talk about this rule is because we kind of use this idea when we talk about the mean value theorem, which is an important theorem. All right. Yeah, I think that's all I want to say about that. Let me, I don't think I have examples of what I want right off the top of my head. That's cool. There was one other thing that she talked about that I thought was really important, and it's this rule. It's that, and I think it's really best, like the way if you draw a picture. So if you have f of x from some a to b, and you break it up at some point c in the middle, it is pretty clear that the integral from a to b of f of x dx, right, the area under the curve from a to b, is equal to the area under the curve from a to c plus the area under the curve from c to b. Now, there is something she said which, although it's true, it doesn't have to be true. And I just want to point this out because she said, and I mean, it makes sense. So certainly this makes sense if we think about A, or I should say, if we think about C being between A and B. But what I actually want to point out is we don't have to have that be true. C could totally, so this formula is also true if your picture looks like this, or if your picture looks like this, which is kind of funky. So, right, check this out. So now what we're saying is the area from A to C plus the area from C to B equals the area from A to B. What? That seems weird, but it's true. So here's what's happening. Let me grab another pen. So here's the area from A to B. Now this pen is not long for this world. Here's the area from A to B. A little better. Does it actually equal the area from A to C, which is all of this, plus the area from C to B? It does, because if you recall, if you integrate in the wrong direction, if you integrate from right to left, you can change the order, but you have to negate it. So what's happening here is that this part here specifically, this is really equal to the negative of the integral from b to c of f of x dx. And then it makes total sense that this part here in green is the total part. I should use red here, sorry. Let me use red here. So this part here in green, let me identify the colors. This part in green for this bottom one is equal to the total thing in blue. That's the integral from A to C. And then we have to subtract off the integral from B to C. But that's exactly what we're doing, because if we're adding the integral from C to B, that's the same as minus the integral from B to C. So all I really want to say about this is that although it makes visual sense for the place you're breaking up an integral to be between the two endpoints, it actually technically doesn't have to be, which is neat. But yeah, we often use this rule to make an improper integral more doable. Sometimes it's just nice to break up an integral as I'm putting the machine. What time is it? Okay, I got time. Yeah, then people like to ask questions about this, like, for example, I'm going to try and make something up. So if the integral from 1 to 3 of f of x dx is equal to 4, and the integral from 1 to 7 of f of x is equal to 19, then what's the integral from 3 to 7 of f of x? No, that'll be fun. Of 9 f of x plus 2. Okay, so if I was trying to tackle this problem, I would draw some pictures. So I know I've got the following. I'm going from 1 to 3 and 1 to 7. So 1, 3, 7. I know the area under the curve from 1 to 3 is 4. I know the total area under the curve from 1 to 7 is 19. So whatever is here, 4 plus it has to equal 19. Well, that's not too hard to figure out. 19 minus 4 is 15. So I like to draw a picture for these kinds of problems because then it makes it pretty easy to figure out. So then we have to break this integral up. I'm going to do the integral from 3 to 7 of 9 times f of x dx plus the integral from 3 to 7 of 2 dx. This 9 that's a constant we can pull out in front of the integral, just like with derivatives, right? Remember with derivatives, we take the derivative of a constant times a function, and we just kind of pull the constant out in front, or the constant would hang out, as I like to say. The same thing is true with integrals. If you're integrating a constant times a function, the constant just gets to hang out. And if we're integrating this, well, the area under the curve from 3 to 7 of f of x is 15. So we're getting 9 times 15 plus, all right, somebody tell me, what's the area under the curve y equals 2 from 3 to 7? I'll give you a hint. It's my favorite number.
2.
It's more than 2.
14.
So say it one more time.
14.
I see where you're getting 14 because I think you're going from 0 to 7 and you're getting 7 times 2. So let me ask you guys a different question. What's the length of the interval from 3 to 7?
3. Well, it's 4.
Right.
4 times 2.
Right. It's 4 times 2, which is 8. Because so here's what we've got. Here's the picture of what we've got. Right. Here's our y equals 2. And we're going from 3 to 7. So our rectangle has a height of 2 and a base of 4. Or we could use the formula, right? The formula says if you're integrating a constant, it's the function, the constant, times b minus a. But I think I never think about this formula really. I just think about what does the picture look like. Oh, it's a rectangle. The base is 7 minus 3. The height is 2. So the area is 4 times 2, which is my favorite number. So I end up with 9 times 15, which is something 135 plus 8, which is 143. Okay, let me ask you guys this. I feel like, so I was looking at your homework before, and some of your problems seem strange in the context of not having learned the fundamental theorem of calculus yet. So I just kind of want to prepare you guys to work on these. So here's the version I have. I know that they all come out a little bit different. So here's problem 2 from the homework, just so you guys are aware of it. They're giving you this. So fact. This is a fact. The integral from 0 to a of x squared dx is equal to 1/3 a cubed. That's true. For example, if I said, what's the integral from 0 to, let's pick a nice number like 3 of x squared, it would equal 1/3 times 3 cubed, which is 1/3 times 27, which is 9. And we could actually look at that, right? If we look at Desmos for a second. Actually, now I'm curious. I don't actually know how you use Desmos to calculate area. You can figure it out together, maybe. But I can definitely look at, if I want to find just the curve, right? Y equals, what have I got there? X squared from 0 to 3. I mean, I know you guys know what x squared looks like. But we can also, you can do some cool things, right? You can say, I want, that's not what I want. If you use a brace, you can say, I want x to be between 0 and 3. And then if you want, you can actually say, oh, there's another way to do this. Oh, I know what it is. Yeah, I want that, but I also actually want to get the area. You can do some kind of fun things. There we go. That's what I was trying to do. So there's actually the region. And sadly, I don't think you can use Desmos to calculate this without knowing more than I do. But that is the area we've got. And it is 9 square units. How nice. So that's not the weird part. The weird part is, that then they're going to ask you questions like, okay, well, this first one isn't so bad, right? So the first one they asked is something like, let me change it a little bit. What's the integral? In fact, let's do this one. What's the integral from 0 to 4 of 1/4 x squared? Well, that's not too terrible. We know we can pull out the 1/4. Right? Constant multiples just hang out. And then we know that the integral from 0 to a of x squared is 1/3 times a to the third. So this is going to be the integral from 0 to 4 of x squared is going to be 1/3 times 4 to the third. And then we could make it a little easier. You can cancel a 4 here and a 4 here. So you get 1/3 of 4 squared, which is going to be 16 over 3. That one's not so funky. But the next one's funky, I think. So here's what the next one's asking. And yeah, I'm going to erase here because I don't want to go somewhere else. So the next one is asking us to calculate something like the integral from -6 to -4 of 6x squared. So first things first, I'm definitely going to pull out the 6. But now here's the issue. I know that the integral from 0 to something of x squared is equal to 1/3 times that something cubed. Neither of these have a lower limit that's a 0, and that's a problem. So here's what we're going to do. We're going to break it up at 0. Now, this is where the thing I was saying before actually is important. We can break this up at 0, even though 0 isn't between them. So check this out. This is equal to 6 times, I'm just stopping at 0 in between, which I know really isn't in between, but that's okay. The integral from -6 to 0 of x squared plus the integral from from 0 to -4 of x squared. If you want to break up an integral from somewhere to somewhere, you're always going from the bottom place to the place you broke it up at, and then from the place you broke it up at to the top place. Now, couple things. Thing one, this is kind of out of order as far as I'm concerned, right? Not actually, I will say this is really in order, right? Like this looks like what I would like it to be. Oh, I wonder if, I just thought of another way you can do this problem, but we'll talk about that in a second. But you can totally switch these and change the signs. So this is equal to 6 times negative the integral from 0 to -6 of x squared dx plus the integral from 0 to -4 of x squared. And now both of these are in the format that we know what to do with. We can say that this is equal to 6 times -6 cubed over 3 plus -4 cubed over 3. Kind of funky. Yeah. And then we can calculate this. This is going to be -6 cubed is -216. but then it's positive, and then divided by 3 is going to be 72 plus 64 over 3. I don't really think we need to simplify anymore. And that's one of the nice things about web work, right? You don't have to simplify your answer fully. You could totally input this and be fine. Sorry, excuse me. I did just have a thought, though, that there might be another way they want you to do this problem, which is perfectly fine. Now, this only works specifically because of the symmetric nature of the graph of x squared. If I was trying to find the area under x squared from -6 to -4, that would be the same as finding the area under the curve from +4 to +6. So another way you could tackle this problem is to say that, oh, the integral from -6 to -4 of 6x squared dx is equal to the integral from 4 to 6 of 6x squared dx. That would also be totally valid. And then you could write this as the integral from 0 to 6 of 6x squared minus the integral from 0 to 4 of 6x squared. And the way I'm getting that is I'm saying, hey, I want this. So I'm going to do draw this part first. I'm going to do this part in red. All of it from 0 to 6 minus this part in green. So we can do it that way. Yeah. And I should point out, just because I feel like I have to point this out now, you could have written this as the integral from 4 to 0 of 6x squared dx plus the integral from 0 to 6 of 6x squared dx. This part here is totally that part there, and this part here is totally that part there. Because if you switch these, you have to have a minus sign. Kind of cool. What time is it? Oh, it's almost time to be over. There was something else I wanted to mention. Oh, yeah. So there's a couple other weird problems. They all kind of require you to do the same sort of thing about kind of reimagining what parts you actually have so that you can write it as 0 to something. There's another one that's the integral from, instead of from -6 to -4, it's from -6 to +4 of x squared dx, let's just say. And if I was doing that one, then I'd be trying to get all of this area. It really is worthwhile to draw a picture. But for this one, I think it's not too hard to see that it totally visually makes sense to break it up at 0, right? You can do the integral from -6 to 0 of x squared dx plus the integral from 0 to 4 of x squared dx. This one, we know the formula. That's going to be 4 cubed over 3. This one, you would have to turn it around, right? This one you could write as the integral from 0 to -6 of x squared dx, but then it's the negative of that. Last thing. So there is one other interesting homework question. And I think on Friday we'll start talking about the fundamental theorem of calculus, which is not that it's not good to know how to do integrals this way, but there are nicer methods that we're going to learn about. But the last thing I want to say is there is a question that's something like this. It wants you to find a that maximizes the integral from 0 to let's pick something nice. Let's pick something terrible, like 19 minus x squared. I just want to show you what they're getting at here. So there are lots of ways to maximize a thing. When I first saw this, I was like, oh, I should take the derivative as a function of a and then try and figure out what makes it equal to 0. Because that's how we used to maximize things, right? We took the derivative, set it equal to 0. And that is something that could be done here if we had the tools, which we will have like next week. Maybe we'll revisit this problem then. But for now, the idea is to think about it graphically. So here's my function, 19 minus x squared. It's just a parabola that opens downwards and has been shifted up 19. So it's got a y-intercept of like 0, 19. It does something like this. And it has an x-intercept of square root of 19, comma 0. I don't care about the left side because I'm going from 0 to a. So check this out. If a is somewhere like here, well, clearly, the integral from 0 to a could be bigger, right? Because the integral from 0 to a is just the amount of area that's under the curve. So I could definitely keep going to the right and get more area. But the problem here, or the thing to recognize here, is that if we go too far to the right, like if we go over here, then we're going to capture all of this area. That all counts as positive. But if we go past this x-intercept, we also have to count this area, but that gets counted as negative. So I think you guys can see that, oh, we want to go as far as we can to capture all of the positive area, but we don't want to go any further than that. That's going to give us some of the negative area. So that